So welcome to the solutions lectures. So there will be 4 of these, and before we get started, I'd like you to start creating a glossary for solutions as we go along. And you'll write your own words and the definitions for those terms in the glossary, and this will help you with revision of this topic. So to start with, here are 5 words that you can add to your glossary early on. If you want to do that now and think about how you would define these before we start the lecture, that would be a good start. So pause the video and have a go at creating your own definitions of these 5 terms. So in solutions 1, we're going to be looking at drug solubility, and the lecture will link to work that you do looking at improving solubility of poorly soluble drugs that you do in part 2 in PM2B. And we're going to look at dissolution. How does a material dissolve? There'll be some thermodynamic concepts here, and we are going to look at a few equations as we go on as well, linked to the topic of solubility. So these is the terms that I gave you at the beginning of the lecture. And here I have provided my definitions of those terms, so you can have a look and see if you have got definitions that are similar. And during these lectures, I'm going to add words, or suggest that you add words to your glossary. And I will not normally provide the definitions, and this is because I want you to define the terms using your own words as we go along. So these lectures are essential for you to be able to understand drug absorption, as all active pharmaceutical ingredients, APIs, must have some solubility in an aqueous environment to be able to have therapeutic activity. We need them to be able to be separated at a molecular level to dissolve and thus be able to cross a membrane. But unfortunately, many new potential drug molecules have poor water solubility. So we need to understand what controls solubility and how we can manipulate the system to improve solubility. So how do we express solubility? There are a number of different ways and units we can use to define how much of a material can be dissolved in a solvent. In other words, what is the maximum concentration of the dissolved material above which it would remain solid and lead to precipitation? Terms you have seen before all work: molarity, molality, which is moles per kilogram, and gram of active material in a milliliter of solvent, so grams per mole, percentage or parts. In this table, we have another way of defining solubility: amount of solvent needed to dissolve 1 gram of solute or drug. So if you need a small amount of solvent, the solubility is very high. And if you need 10,000 grams of solvent to dissolve 1 gram of drug, the material is practically insoluble. And with this, we have a formal terms to define solubility. Our solid powder of our active ingredient will be made up of molecules that will be held together by intermolecular forces. To dissolve in water, every one of these molecules needs to separate from that lattice and interact with water molecules. The process of dissolution involves breakage of solute-solute and solvent-solvent bonds, both endothermic processes, and the formation of bonds between solute and solvent with the liberation of energy. For dissolution to occur, delta G must be negative, and thus there must be a balance between the enthalpy of dissolution and the associated entropy. Solubility of a chemically related series are inversely related to their melting points, because the removal of solute molecules from solid reflects the strength of interaction between the solute molecules within the solid. So how easily, from an energetic point of view, that solid can melt. From a structural point of view, you may know already the impact different functional groups have on solubility in water. Substituent groups such as polar groups impart high solubility due to capability of strong bonding with water, so the delta H for the solvent-solute bond is negative. And for non-polar groups such as CH3, they will impart very low solubility because of the poor interaction between the solute and the solvent. And there are many other examples of different functional groups that we will go through on later slides. We now know that changes in delta H for breaking the lattice structure and delta H for solvation often lead to an overall positive change in terms of delta H. So the dissolution is usually controlled by an entropy change. Okay, and this means that T delta S has to be larger than delta H, the delta H term, if delta G is going to be negative, as you can see here. So what this means is if forces holding our solute molecules together are very strong compared to forces that hold or that would link a solute molecule to a solvent molecule, then the solute won't break down and form a solution. And if the forces that hold the solvent molecules together in the solvent are very strong compared to the forces between the solvent and the solute, then the solvent won't accept the solute molecule, so won't accept the absorbing molecule. If forces that hold the solvent and the solute molecule are greater than those that are holding the solute molecules together and the solvent molecules together, then we will get dissolution and the solute will dissolve in the solvent. And we saw that on our previous slide. The properties of a solvent and a solute that impact on solubility are listed here. First of all, let's look at the solute. First of all, the melting point of the solid will have an impact and will link to solubility. Melting is the process of breaking the intermolecular bonds in the particles in the crystal to melt the structure. So the melting point does relate to the strength of the intermolecular interactions. And as we know from what we've just said, solubility also relates to the strength of the intermolecular interactions between the molecules within the lattice. So melting points can be used to predict solubility. We can also see that the crystal structure, and particularly the molecular structure, will have an impact. And you know that molecular structure in terms of the functional groups will impact on solubility, and crystal structure also will. So what kind of form the molecules are held together in the solid form. And things like particle size as well will come across later. And there are also properties of the solvent to think about, such as temperature, pH, and what the solvent is made of. Are there any co-solvents or other additives to our solution that could impact on the solubility of our active ingredient? Let us consider the crystal lattice first. In a crystal, molecules are packed in a repeating three-dimensional arrangement. And some molecules, lots of drugs, can pack in different arrangements. So there's not one lattice structure that a solid can form. Many can form multiple different structures. Each arrangement will have a different intermolecular forces, which means they'll have a different delta H lattice for each of the different ways that the molecules can arrange in the crystal structure. And this will affect the dissolution rate and have impact on physical properties of your drug, of course, including solubility. These different crystal lattice structures of the same material are called polymorphs. Now, for an atom, for example, carbon, you already know that carbon can form graphite, diamond, and other structures by forming different intermolecular structures known as allotropes. Polymorphic structures are when a molecule can form more than one type of lattice, crystal lattice, and due to the different physical properties of the polymorphs, just like the different physical properties of diamond and graphite that are formed by carbon, these different structures can be able to make them have different stabilities and have other properties that are different, that are very important commercially, of course, including solubility. A solid material can also form a solvate, and this is where the crystallizing drug contains water, and in that case it would be called a hydrate, that becomes incorporated in the crystal lattice of the material. And by having water within the crystal lattice, by having a hydrate, you decrease the solubility of the lattice in water. Remember, solubility will depend on the relative energies, and if the delta H lattice is strengthened, then the solubility will be reduced. Finally, a term I mentioned briefly before, which is amorphous. And amorphous solids have no regular lattice. Their structure is completely random. So that means they have no delta H lattice. Delta H lattice will equal 0. And so if your solute is in a solid form that is amorphous, then this is going to increase the solubility of that solute. So let's look at some of the terms that we've introduced here: crystal structure, polymorph, solvate, hydrate, amorphous. So these are terms that you could add to your glossary. Think about what we said about those terms and provide your own definition. If you want to do that now, pause the video here to do it, and we'll continue to add terms to your glossary as we go. Moving on, we have briefly mentioned the importance of chemical structure of the solute. That's the active ingredient in terms of solubility. Small changes in a molecule can result in significant changes in solubility. Looking for an example, phenol, a derivative of benzene, the addition of OH group makes this 100 times more soluble in water because it now has a functional group that can interact via hydrogen bonding with water. Another example, sodium salicylate, is 500 times more soluble than salicylic acid, and that's due to its ionization. So the salt form there is 500 times more soluble than the acid. We saw the impact of the sodium salt for the case of salicylic acid, increasing the solubility of the active ingredients by 500 times. Many drugs are weak acids or weak bases. So weak acids, which have a COOH group, for example, and a weak base with an amine group, so CH2. A weak acid can form a salt, for example, a sodium salt, and this is a method used to increase solubility or stability of a drug. This example here is amitriptyline hydrogen chloride. The chloride salt, the drug used in formulation to improve solubility. If you look in the BNF, you will see many drugs that are formulated in their salt form, as sodium or potassium salts if they are weak acids, and as hydrogen chlorides if they are weak bases. If drugs are weak electrolytes, their solubility changes with pH. Weak electrolytes represent the vast majority of active ingredients. The solubility increases with degree of ionization. So as you can see here, percentage ionization against pH, the percentage ionization is equal to the percentage of maximum solubility. So you can see that for an acidic drug, then the percentage ionization increases with pH, and for a basic drug, the percentage ionization and therefore the solubility decreases with pH. And also, if we know the pKa of our drug, then we can see that at the pKa we have 50% dissociation of the weak electrolyte, and for 2 pH units either side of the pKa, then we have partial dissociation. So that means we have both ionic and non-ionic form of the drug present in solution. This actually means that the solubility of the drug changes with pH, and this also impacts on absorption of the drug, which we'll talk about in later lectures. Looking at this example here in a bit more detail, we have acetic acid here. So you can see that it's very low ionization at low pH, and then as you increase the pH, then the acid becomes charged, it forms its ionized form, and then that increases that increase in ionization will increase its solubility. So it has the lowest solubility at low pH and higher solubility at high pH. And remember, high pH has low hydrogen concentration, and so that's why the acid is ionized. It loses its H+ at high pH, whereas low pH has high hydrogen ion concentration, and so the acid keeps its hydrogen. I think it's important at this stage to talk a bit about buffer action. So buffers will be very important for controlling the pH of our solvent system, and as you can see, that could be very, very important for controlling the solubility. What is a buffer action? So a buffer is an example of a weak acid and a conjugate base. The conjugate base provides the ions at appropriate high concentration. For this example here, the acetate ions at high enough concentration. And the acid is in equilibrium in ionized and unionized form. And it shifts to account for the ions coming from the conjugate acid, which is the salt, making it that both the conjugate acid and the acid are in appreciable quantities and so able to buffer. This means they can shift the equilibrium of the weak acid when a strong acid or base is added. So this movement between the ionized and the unionized form here allows it to buffer the system and control the number of hydrogen ions and ions that are in the system. There are other properties of the solvent, so you can add things to your solvent that will impact on the solubility of your active ingredient. So for example, you can add salts. And these will modify the solubility. It could result in salting out. When a salt is added to an aqueous solution and the salt competes with the solute for water molecules, it could reduce the solute's solubility. Or the added salt could salt in. Some large anions or cations can increase the solubility by something known as hydrotropism. So hydrotrope is a compound that solubilizes hydrophobic compounds in an aqueous solution. And an example would be adding sodium benzoate to aqueous solution can increase the solubility of caffeine. So as I said, the other additives, the other excipients and components of a formulation can impact on the solubility of the active ingredient. Finally, we can alter solubility of our drug through the use of a co-solvent. And here you can think that like dissolves like. So a solvent dissolves best in a solute, dissolves best in a solvent with similar chemical properties. So a polar compound will dissolve better in a polar solvent. And a non-polar compound will dissolve better in a non-polar solvent. By adding a co-solvent to water, you can improve the extent to which it is able to dissolve a non-polar substance. So this is useful where you have a poor water-soluble drug. And therefore, if you add a co-solvent to water that is slightly less polar than water, then it might provide the environment that allows that non-water soluble drug to dissolve. And an example here is diazepam, with this 5 mg per ml injection, will be in water and ethanol, and it has solubility in water alone that is significantly lower. So its solubility is improved by the presence of ethanol. Finally, here's some more terms that I have introduced through the lectures, this lecture that you can add to your glossary at the end of the lecture. In the summary, this is what we have spoken about in this lecture. We know that solubility is very complex, and that is a really important property of a drug for the drug to have therapeutic action. And it will depend on properties of the drug molecule itself and also properties of the solvent and the environment that the drug is dissolving in.